There is a persistent myth in software engineering. It's the belief that high-level programming languages abstract away physical hardware, making the silicon somebody else's problem. In embedded systems, that abstraction is a dangerous illusion. The programmer is directly exposed to and strictly bound by the physical limitations of the processor. Over 10 billion embedded systems deployed worldwide run on ARM cores. These chips strictly dictate how code must be written to survive on them. To save power and physical die space on the silicon, a massive portion of these microcontrollers completely lack a hardware floating point unit. They are built with only an integer arithmetic logic unit. Compiling standard C floating point mathematics for an integer-only chip forces the compiler into software emulation. This consumes thousands of extra clock cycles and destroys real-time performance. We are forced to process continuous, real-world measurements, like analog temperatures or voltages, on a machine that physically cannot comprehend decimals. The engineering workaround for this hardware deficiency is fixed-point arithmetic. We implement this by applying a scale factor. A scale factor multiplies a continuous decimal value by a predetermined constant, shifting the decimal point to the right until the number can be safely executed as a whole integer. The compiler will not handle this for you. The developer must manually architect the scaling logic directly into the code. To meet strict execution deadlines, the programmer has to abandon the comfort of high-level math and manually map their equations on the hardware's integer logic. This diagram breaks down how we mathematically project from the real domain, lowercase x, to the integer domain, uppercase x. The formula is strict. X equals the rounded product of our input x and its scale factor. Assume we are reading a sensor that outputs a value between 0.1 and 1.0. To secure 2 decimal digits of precision without using floating point types, we apply a scale factor of 100. If the sensor reads 0.7, multiplying by 100 drops it safely into the register as the integer 70. This projection creates a physical artifact on the chip, a deadband. Because our real input never drops below 0.1, the corresponding integers 0 through 9 will never be generated. That specific block of integers represents permanently wasted register capacity. Gaining mathematical precision inherently costs us physical data space. With the base input scaled, we can execute complex operations, starting with mathematical inversion. The goal is to take our scaled integer input, x, and compute a scaled integer output, y, while ensuring the ALU never encounters a fractional value. By substituting our scale factors into the standard inversion equation, we derive a pure integer formula. Y equals the product of the x and y scale factors divided by x. Looking at our data table, let's test a real input of 0.4, which we have already scaled to an integer x of 40. We multiply our input scale factor of 100 by our output scale factor of 10, giving us 1,000. Dividing 1,000 by our integer input of 40 yields an output integer of 25. If we remove the output scale factor of 10 from that 25, we return to a real domain quotient of 2.5.
The integer mathematics accurately mirror the real domain inversion, but there is a hardware trap hidden in the numerator's combined scale factors. The formula requires multiplying the two scale factors together. If that product is exactly 1,000 and the processor's radix complement representation maxes out at 999 for that specific register, an overflow will occur. The engineer must manually lower the constant to 999 in the code, intentionally sacrificing a fraction of precision to prevent a system crash. Moving from inversion to division drastically escalates to risk. Division requires tracking and balancing 3 interacting scale factors simultaneously, one for the numerator, one for the denominator, and one for the final quotient. This generates our final integer divider formula. Q equals the combined scale factors divided by the quotient scale factor, multiplied by x, and then divided by y. The strict order of operations dictated by those brackets is critical. If the compiler executes the steps in the wrong sequence, the intermediate values will exceed the register limits and overflow during the ALU execution. Let's apply this to a high-precision scenario requiring 4 decimal digits for the quotient, using an input x of 0.50 and an input y of 0.25. In the processor, x becomes the integer 50 and y becomes 25.
Tracking through the carefully bracketed equation, the ALU computes an integer result of 2000. By dividing that integer 2000 by the massive quotient scale factor of 10,000, we perfectly retrieve the exact real quotient of 2.00. The fixed point division architecture holds. We have mathematically solved the division problem, but we have introduced a severe performance penalty. Standard integer multiplication and division instructions are computationally expensive. Running them continuously will cause the processor to bottleneck. The final optimization requires abandoning decimal scale factors, powers of 10, in favor of binary scale factors, based on powers of 2. Aligning our scale factors to powers of 2 allows us to replace the expensive division instructions with ultra-fast single-cycle bit shifts at the hardware level. Perfect mathematical accuracy means nothing if the system misses a real-time execution deadline. The algorithm itself must be contoured to the specific latency limits of the chip's instruction set. This optimized C code for fixed-point inversion uses bit shift constants. The mathematical model collapses into one operational line, instantly manipulating the register's physical electrical state. This small block of code serves as a direct physical mapping of the hardware's data pathways and latency limits. High-level software abstraction is a luxury that embedded engineers simply cannot afford. Writing safe, performant code on these devices requires an intimate knowledge of exact register bit widths and processor-specific radix limits. The software engineer is operating fractions of a millimeter away from the bare metal of the processor. They are navigating the exact microscopic boundary where typed software logic instantly translates into pure physical electrical states. Embedded engineering requires architecting mathematical solutions that can survive the brutal constraints of the silicon.